In August 2023, NASA lost contact with Voyager 2, not for seconds, not for minutes, for months. The spacecraft was 41 light hours from Earth, deeper in space than any human-made object except its twin, Voyager 1. It had been traveling since 1977, 46 years in transit, and then, because of a sequence of commands that accidentally tilted its antenna 2 degrees away from Earth, it went silent. The silence lasted from July 21 to the 4th of August 2023, 12 days during which Voyager 2, the only human-made object to have passed through the heliopause into interstellar space while transmitting science data, was unreachable. The Deep Space Network sent commands into the void and received nothing back. Then, on August 4, engineers at the Deep Space Station in Canberra, Australia, transmitted a command using the highest possible power, setting 100 kilowatts directly toward where they calculated Voyager 2 should be. They waited 41 hours for the signal to travel there and another 41 hours for a response to return. 82 hours total. More than 3 days just for the round trip of a single radio signal. And on August 4, before the response even arrived, the Deep Space Network picked up something unexpected. Voyager 2's own faint carrier signal, barely above the noise floor, confirming the spacecraft was still alive and still transmitting. The antenna had drifted, but Voyager 2 was still there, still working, still sending data from beyond the edge of the solar system. On the 15th of October 2023, NASA announced that communications had been fully restored. Voyager 2 was back online, transmitting science data again from interstellar space. But here is what I want to talk about. Not the drama of the lost contact, but what Voyager 2 has been measuring out there beyond the boundary of the sun's influence in the region of space that no probe has ever visited before in human history. Because the data that comes back from Voyager 2's position is not just engineering telemetry. It is science from a frontier that no telescope can see, no theory has been fully tested against, and where the physics of our solar system ends and the physics of the galaxy begins. The data is terrifying not in the science fiction sense of alien signals or existential threat. It is terrifying in the more profound and more honest sense. It tells us how alone this solar system is, how thin and fragile the bubble of the sun's influence actually is, and what conditions are like in the vast ocean of interstellar space that constitutes most of the universe's volume. Let me take you through what Voyager 2 has found, what those findings mean for physics, and why the picture that emerges from the boundary of the solar system should change how you think about Earth's place in the cosmos. Let me start with the heliosphere, because understanding what Voyager 2 has crossed requires understanding what it left behind. The sun is not just a source of light and heat. It is a source of a constant stream of charged particles, the solar wind, that flows outward from the sun's corona in all directions. The solar wind consists primarily of protons and electrons, with a small fraction of helium nuclei and traces of heavier ions. At Earth's orbit, the solar wind has a speed of approximately 400 to 700 kilometers per second and a density of approximately 5 to 10 particles per cubic centimeter. At the orbit of Pluto, 40 astronomical units from the Sun, the density has fallen to approximately 1 particle per 10 cubic centimeters. The solar wind is not constant. It varies with the 11-year solar activity cycle, with faster and denser wind during solar maximum and slower, thinner wind during solar minimum. It also contains faster, denser streams from coronal holes in the sun's atmosphere, which can overtake and collide with the slower background wind, creating co-rotating interaction regions where the plasma is compressed and heated. At Earth's orbit, these structures interact with the Earth's magnetosphere, driving geomagnetic storms and auroras. The solar wind exerts a pressure on the surrounding interstellar medium. This pressure, plus the pressure of the sun's magnetic field carried by the solar wind, inflates a bubble in the surrounding interstellar gas, the heliosphere. The heliosphere is bounded by the heliopause, where the total pressure of the solar wind equals the total pressure of the interstellar medium. Before reaching the heliopause, the solar wind passes through the termination shock. The solar wind is supersonic at all distances from Earth's orbit out to the termination shock. At the termination shock, the solar wind abruptly slows from approximately 400 kilometers per second to approximately 150 kilometers per second, converting kinetic energy to thermal energy and compressing the plasma. The region between the termination shock and the heliopause is the heliosheath, a turbulent region of decelerated, heated solar wind plasma. The shape of the heliosphere is not spherical. The sun is moving through the local interstellar medium at approximately 23 kilometers per second in the direction of the constellation Hercules. This motion compresses the heliosphere in the direction of motion, creating a blunt nose, and stretches it behind, creating a long tail called the heliotail. The nose of the heliosphere, where Voyager 1 crossed the heliopause in 2012, is at approximately 122 astronomical units. The side boundary, where Voyager 2 crossed in 2018, is at approximately 119 astronomical units. Voyager 1 crossed the termination shock in 2004 at approximately 94 astronomical units. Voyager 2 crossed it in 2007 at approximately 84 astronomical units. The difference in crossing distances between Voyager 1 and Voyager 2 reflects the asymmetry of the heliosphere at different latitudes and the time variability of the solar wind output between the two crossing epochs. Voyager 2 crossed the heliopause on the 5th of November 2018, confirmed by a sharp increase in the intensity of galactic cosmic rays measured by the Cosmic Ray Subsystem Instrument, and a sharp decrease in the intensity of energetic particles from the Sun measured by the Low Energy Charged Particle Instrument. The Plasma Science Instrument also measured a sharp increase in the electron density from the low-density heliosheath plasma to the higher-density interstellar plasma. The crossing was at approximately 119 astronomical units from the Sun, at a latitude of about 30 degrees south of the solar equatorial plane. This is the point where Voyager 2 officially left the solar system and entered interstellar space. The crossing also revealed something specific and significant: the temperature of the plasma in the heliosheath just before the heliopause was approximately 30,000 to 50,000 Kelvin, substantially hotter than the roughly 20,000 Kelvin predicted by the standard heliospheric model. This excess temperature suggests energy deposition by charge exchange between solar wind protons and interstellar neutral hydrogen atoms that penetrate the heliopause, a process not fully accounted for in standard models. If the scale of what Voyager 2 is measuring the edge of the Sun's influence at 119 astronomical units, the fragility of the bubble that makes our solar system possible is already changing how you see our place in the cosmos. These are exactly the kinds of perspectives I explore in my book. Ready to change how you see the world? Get your copy of 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. The data Voyager 2 has transmitted from interstellar space tells us things about the boundary between the solar system and the galaxy that we could not have known any other way. The first finding is about the structure of the heliopause itself. Before Voyager 2 crossed, the standard model of the heliosphere predicted that the heliopause would be a relatively sharp boundary, thin compared to the scales involved. Voyager 1's crossing in 2012 suggested the heliopause was indeed relatively thin, though with complications. Voyager 2's crossing in 2018 revealed something different: a narrow region of elevated electron density and temperature just inside the heliopause, which the science team called a heliosheath depletion region. This region, approximately a few astronomical units thick, showed evidence of magnetic reconnection, the process by which magnetic field lines from the solar wind and the interstellar medium meet, break, and reconnect in new configurations, releasing energy. Magnetic reconnection at the heliopause has implications for how the solar wind's energy is dissipated and how interstellar neutral atoms penetrate into the inner heliosphere. Some fraction of these interstellar neutrals travel through the heliosphere and can be detected inside Earth's orbit. The IBEX spacecraft, which stands for Interstellar Boundary Explorer, has been measuring these interstellar neutral atoms since 2008 and has revealed a complex structure in the boundary, including the controversial IBEX ribbon, a narrow band of energetic neutral atoms that does not fit simply into any current model of the heliosphere. The second major finding from Voyager 2's interstellar data is about the local interstellar magnetic field. Before any spacecraft crossed the heliopause, our understanding of the direction and strength of the local interstellar magnetic field came from indirect measurements, the deflection of cosmic rays, the properties of the IBEX ribbon, and polarization measurements of starlight. Different methods gave somewhat different answers. Voyager 2's direct measurements in interstellar space provide a definitive measurement of the local interstellar magnetic field direction and strength. The measurements show that the interstellar magnetic field makes an angle of approximately 30 degrees with the ecliptic plane of the solar system, which is consistent with some models but not others. The field strength is approximately 5 nanotesla, about 100,000 times weaker than Earth's surface magnetic field. The direction of the local interstellar magnetic field has implications for the overall shape of the heliosphere. If the magnetic field were strongly draping around the heliosphere, it would create a more elongated shape in the direction of the solar motion. If it were more perpendicular to the solar motion, it would create a more rounded shape. Current data from Voyager 1, Voyager 2, and IBEX suggest a heliosphere that is more rounded than the comet-like shape that was the standard picture for decades. The third major finding is about the cosmic ray environment in local interstellar space. Galactic cosmic rays are high-energy charged particles, predominantly protons and helium nuclei, that have been accelerated in supernovae and other violent astrophysical events throughout the galaxy. They permeate the galaxy's disk and fill the heliosphere at a reduced flux because the solar wind and the heliospheric magnetic field deflect and reduce the flux of cosmic rays below about 100 MeV per nucleon. Outside the heliopause, Voyager 2's cosmic ray instruments measured the full, undepleted cosmic ray spectrum below energies that had been partially blocked inside the heliosphere. The measurements show that the heliosphere provides significant shielding against low-energy cosmic rays, reducing their flux inside the heliosphere by a factor of a few compared to outside. This shielding matters for the habitability of Earth because low-energy cosmic rays penetrate the atmosphere and contribute to the radiation environment at the surface. Without the heliosphere, the cosmic ray flux at Earth's surface would be higher. I described in the Proxima Centauri b video how important the heliosphere is for planetary habitability. The heliosphere provides a global magnetic environment that deflects cosmic rays from the inner solar system. Planets around stars without a strong stellar wind or without the right stellar wind parameters to create a large heliosphere would have higher cosmic ray backgrounds. The heliosphere is one of the factors that makes the Earth's surface a relatively benign radiation environment compared to what it would be in the raw interstellar medium. The fourth major finding concerns the density and temperature of the local interstellar medium. Before the Voyager crossings, we knew from UV absorption spectroscopy of nearby stars that the Sun is located in a region of the galaxy called the Local Interstellar Cloud, a region of warm, partially ionized hydrogen gas with a density of approximately 0.2 to 0.3 hydrogen atoms per cubic centimeter and a temperature of approximately 6,000 to 7,000 Kelvin. Voyager 2's plasma science instrument, which is still operating, unlike Voyager 1's plasma instrument, which failed in 1980, has measured the electron density and temperature in the local interstellar medium directly. The measurements are consistent with the pre-existing models, a warm, partially ionized plasma, but the specific values, combined with the magnetic field measurements, constrain the pressure balance at the heliopause more precisely than any previous measurement. The pressure balance between the solar wind and the interstellar medium determines the size of the heliosphere. A denser or warmer interstellar medium would compress the heliosphere to smaller radii. A less dense or cooler medium would allow the heliosphere to expand. The current heliosphere, with its heliopause at approximately 120 astronomical units, reflects the specific balance between the sun's output and the local interstellar environment. This balance is not constant over astronomical time. As the sun moves through different regions of the galaxy during its orbit, it encounters interstellar clouds with different densities and temperatures. When the sun passes through a denser cloud, the heliosphere is compressed. When the heliosphere is compressed to small enough radii, say a few astronomical units instead of 120, the cosmic ray flux in the inner solar system increases significantly. Some researchers have proposed that passages through dense interstellar clouds contributed to ice ages on Earth by increasing the cosmic ray flux, which seeds more cloud formation in the Earth's atmosphere. The evidence for this mechanism is indirect and contested, but it illustrates the connection between the local interstellar environment and conditions on Earth. What Voyager 2 is revealing is that the Sun and the heliosphere are not isolated. They are embedded in a galaxy that affects them, and through them, every planet in the solar system. Understanding the deep interconnectedness of physical systems is one of the 12 principles in my book. Get 12 principles for understanding the fabric of reality at realityprinciples.com. Let me give you the full context of what the Voyager program is, because the engineering and science story behind these spacecraft is as significant as the data they return. Voyager 1 and Voyager 2 were launched within 16 days of each other in 1977. Both designed to take advantage of a rare planetary alignment that would allow them to visit multiple outer planets using gravitational assists. Voyager 2 launched first on the 20th of August 1977. Voyager 1 launched second on the 5th of September 1977, but on a faster trajectory to Jupiter and Saturn. The planetary alignment that made the Grand Tour possible occurs roughly once every 175 years. The last one before 1977 was in 1801. The next one will not occur until approximately 2153. NASA engineers in the 1960s recognized this window and designed the Voyager mission to exploit it. Voyager 2 is the only spacecraft to have visited all 4 outer planets. It flew past Jupiter in July 1979, Saturn in August 1981, Uranus in January 1986, and Neptune in August 1989. At each planet, the spacecraft used a gravitational assist, approaching the planet in a precise trajectory that converted some of the planet's orbital energy into the spacecraft's kinetic energy, boosting Voyager 2's speed. Without the gravitational assists, the mission would have taken far more fuel or would have been limited to fewer planetary encounters. At Neptune, Voyager 2 flew within approximately 4,950 kilometers of the cloud tops and 40,000 kilometers of Neptune's largest moon, Triton. The Neptune encounter deflected Voyager 2's trajectory sharply southward relative to the ecliptic plane, which is why it crossed the heliopause at a southern latitude rather than near the ecliptic. The 5 instruments currently operating on Voyager 2 are the Plasma Science Instrument, the Cosmic Ray Subsystem, the Low Energy Charged Particle Instrument, the Magnetometer, and the Plasma Wave Subsystem. The plasma science instrument, which measures the density, speed, and temperature of the solar, wind, and interstellar plasma, is unique. It is still working, whereas the equivalent instrument on Voyager 1 failed in 1980. This makes Voyager 2 the only spacecraft that can directly measure the plasma properties of the local interstellar medium. The data from these instruments is transmitted at a rate of approximately 160 bits per second through the deep space network. For comparison, a home internet connection transmits hundreds of millions of bits per second. Voyager 2's entire daily science data budget fits in a few seconds of home broadband. The signals are so weak, arriving after an 18-hour transit time from 134 astronomical units, that they require the 70-meter dish antennas of the Deep Space Network to detect them at all. The Deep Space Network maintains contact with Voyager 2 using a combination of the Goldstone facility in California, the Madrid facility in Spain, and the Canberra facility in Australia. Contact is scheduled for approximately 8 hours per day. The August 2023 incident, when the antenna tilted 2 degrees away from Earth, illustrated just how narrow the margin of error is. A 2-degree pointing error at a distance of 134 astronomical units was enough to render the spacecraft unreachable for 12 days. Now let me take you to what is perhaps the most scientifically significant finding from Voyager 2's crossing and subsequent measurements in interstellar space. The Voyager 2 science team published a series of papers in Nature Astronomy in November 2019, reporting the detailed measurements from the heliopause crossing. One of the most striking findings was that the temperature of the plasma in the heliosheath, just inside the heliopause, was higher than models had predicted. The heliosheath plasma temperature was approximately 30,000 to 50,000 Kelvin, substantially hotter than the roughly 20,000 Kelvin predicted by the standard heliospheric model. The excess temperature suggests that energy is being deposited into the heliosheath plasma by a process not included in the standard models. One candidate is charge exchange between solar wind protons and interstellar neutral hydrogen atoms. Interstellar neutral hydrogen can penetrate through the heliopause into the heliosheath, where it undergoes charge exchange with solar wind protons. The neutral atom gives its electron to the proton, creating a new fast neutral hydrogen atom that escapes, and a slow charged proton that is captured by the solar wind magnetic field. This process transfers energy from the interstellar neutrals to the solar wind plasma. Another finding concerns the behavior of the magnetic field at the heliopause. The magnetic field in the heliosheath, which is the distorted and slowed solar wind magnetic field, showed a specific rotation pattern as Voyager 2 crossed into interstellar space. The field rotated by approximately 90 degrees as the spacecraft transitioned from the solar to the interstellar magnetic field, consistent with the geometry of the boundary, but revealing the specific orientation of the two magnetic fields at the crossing point. Perhaps most intriguing was the report by the Voyager science team of a thin layer at the heliopause, where the electron density was much higher than either the solar or interstellar values. This electron density spike suggests the presence of a compressed plasma layer at the boundary, where the solar and interstellar plasma meet and the magnetic field is particularly tangled. Understanding this layer requires a detailed model of plasma physics at the heliopause that does not yet exist. The Voyager data also revealed that the transition from the heliosphere to interstellar space is not the same at all locations. Voyager 1, which crossed the heliopause at a different latitude and a different time in the solar cycle, found a somewhat different crossing structure than Voyager 2. This suggests that the heliopause has a complex structure that varies with location and with the solar cycle. The Sun's activity cycle, which affects the solar wind output over the approximately 11-year cycle of sunspot activity, imposes an 11-year modulation on the heliosphere size and on the properties of the heliopause. Let me now connect the Voyager 2 findings to the broader question of what they tell us about the galaxy we inhabit. The local interstellar medium, the region of the galaxy within a few hundred light years of the Sun, has a specific structure that has been shaped by the history of stellar evolution in the solar neighborhood. The local bubble, the large region of hot, thin plasma within which the solar system currently resides, was probably created by a series of supernova explosions approximately 10 to 20 million years ago that swept away the denser interstellar gas and replaced it with hot, low-density plasma. The Sun entered the local bubble approximately 5 to 7 million years ago. Before entering the local bubble, the Sun was presumably in a denser, cooler, interstellar medium with a different heliosphere and a different cosmic ray environment for the planets. The transition into the local bubble may have changed the radiation environment in the inner solar system in ways that affected the evolution of life on Earth. Within the local bubble, there are smaller, denser clouds, including the Local Interstellar Cloud in which the Sun is currently embedded. The Sun entered the Local Interstellar Cloud approximately 10,000 years ago and will exit it in approximately 1,000 to 10,000 years. The transition out of the cloud will change the properties of the local interstellar medium and hence the heliosphere. These are not hypothetical or distant concerns. They are facts about the environment of our solar system on timescales relevant to human civilization. The Sun has been, is, and will continue to be embedded in a dynamic galactic environment that changes the conditions in the inner solar system on timescales from thousands to millions of years. The Voyager 2 data is the first direct measurement of that environment from inside it. Everything we knew before came from remote sensing, from spectroscopy of nearby stars, from the IBEX measurements of energetic neutral atoms, from models of heliospheric physics. Voyager 2 is the first instrument to actually be in the local interstellar medium, measuring the plasma directly. The picture it gives us is of an interstellar medium that is inhospitable to life in ways that are less dramatic than science fiction imagines, but more pervasive. The cosmic ray flux in interstellar space is higher than inside the heliosphere. The magnetic field, while weak, is present and structured. The plasma density, while low, provides a medium through which high-energy particles propagate and in which chemical reactions occur over geological timescales. The heliosphere is a sanctuary. It is a magnetic bubble created by the Sun that protects the inner solar system from the full intensity of the galactic environment. Without it, the cosmic ray dose at Earth's surface would be higher. The chemistry of the upper atmosphere would be different. The habitability conditions would be different. The heliosphere is not just an interesting astronomical structure. It is a physical requirement for the kind of surface environment that life on Earth requires. The heliosphere as a sanctuary, the Sun as a physical requirement for life, not just through its light and heat, but through the magnetic environment it creates, is one of the most profound examples of the deep structural principles that make complex life possible. These principles are at the heart of my book. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. Let me now address the question of what happens to Voyager 2 from here and what that tells us about the limits of our ability to explore interstellar space. Voyager 2 is currently at approximately 134 astronomical units from the Sun and moving at approximately 3.3 astronomical units per year. At this rate, it will take approximately 300 years to reach 1,000 astronomical units. The nearest star, Proxima Centauri, is approximately 268,000 astronomical units away. At Voyager 2's current speed, it would take approximately 81,000 years to reach Proxima Centauri if it were traveling in that direction, which it is not. Voyager 2 is powered by 3 radioisotope thermoelectric generators, RTGs, which convert the heat from the radioactive decay of plutonium-238 into electricity. Plutonium-238 has a half-life of approximately 87.7 years. Voyager 2 was launched in 1977. As of 2024, approximately 47 years have elapsed, meaning the RTGs are producing approximately 70% of their original power output. The spacecraft's instruments draw approximately 250 watts of power. As the power decreases over time, instruments have been and will continue to be turned off to concentrate power on the most important science experiments. The power will drop below the level needed to operate any science instrument sometime around 2025 to 2026, at which point Voyager 2 will become a passive object transmitting only engineering data, if anything. The last science data from interstellar space by a human-made probe will have been received. There is no follow-up mission currently funded or planned to send another spacecraft to the heliopause in interstellar space. A mission proposal called the Interstellar Probe has been studied by NASA, with a concept for a spacecraft that could reach 1,000 astronomical units in 50 years using a solar sail or nuclear propulsion. But no such mission has been approved or funded. The detailed science that Voyager 2 is performing right now, measuring the plasma, magnetic field, cosmic rays, and neutral atoms of the local interstellar medium in situ, will not be repeated in any science mission currently under development. This is the broader context that makes Voyager 2's current transmissions significant beyond their scientific content. They are, for the foreseeable future, the only direct measurements we will have of the environment just beyond the solar system. The data Voyager 2 is sending back right now is irreplaceable. Every year that it continues to transmit is a year of data that cannot be obtained any other way. Let me close with what I think is the most important thing to say about what Voyager 2 has found and what it means. Voyager 2 is, in one sense, the smallest possible step into interstellar space. It is at 134 astronomical units. Proxima Centauri is 268,000 astronomical units away. The fraction of the journey to the nearest star that Voyager 2 has completed is approximately 0.05%. It has taken 47 years to cover this small fraction using the most powerful propulsion technology we have ever applied to an interstellar probe. In another sense, Voyager 2 has revealed everything important about what lies just outside the heliosphere. Not because 134 astronomical units is far, but because the heliopause is the boundary we needed to cross to measure the local interstellar medium directly. The local interstellar medium extends for many light years in all directions. The specific properties that Voyager 2 is measuring, the plasma density, the magnetic field, the cosmic ray spectrum, are the properties that characterize the environment through which any interstellar spacecraft would have to travel. They are the physical facts about the space between the stars that any future interstellar mission must reckon with. What those facts tell us is consistent with what I described in the previous videos about the difficulty of interstellar travel. The interstellar medium is not empty. It contains a magnetic field that deflects spacecraft trajectories at high velocities. It contains cosmic rays that would irradiate any crew. It contains neutral atoms that become energetic projectiles for any spacecraft moving at a significant fraction of the speed of light. It is an environment that is hostile to the kind of travel that science fiction imagines as routine. Voyager 2 is moving slowly enough that none of these effects are significant for the spacecraft. Its instruments are not threatened by the interstellar magnetic field or the cosmic ray flux, but the physics it is measuring is the physics that makes high-speed interstellar travel so difficult. The transmission from deep space is terrifying not because of what it says about threats from outside, but because of what it says about the scale of the universe and the smallness of our reach into it. Voyager 2 took 47 years to cross the heliosphere, traveling faster than any human-made object in history at launch. It has reached 0.05% of the distance to the nearest star. The universe is not waiting to be explored. It is vast, governed by physics that sets severe limits on how fast we can move and how far we can reach. And the data coming back from Voyager 2 is a precise measurement of those limits. Every signal that arrives from 134 astronomical units away after an 18-hour transit time is a dispatch from the only outpost humanity has ever established beyond the solar system. It is the most distant measurement in history, and it tells us with extraordinary precision what we are surrounded by and how far we have to go. Voyager 2's journey, the fact that 47 years of travel has covered 0.05% of the distance to the nearest star, is one of the most concrete demonstrations of what the fabric of reality actually allows. That kind of grounding in physical reality, understanding what is possible and what is not and why, is the foundation of my book, Ready to Change How You See the World. Get 12 principles for understanding the fabric of reality at realityprinciples.com. What do you think Voyager 2's data tells us about our place in the cosmos? Tell me in the comments. If this changed how you think about Voyager 2's transmissions and what they mean for our understanding of the solar system and the galaxy, tell me in the comments. Tell me whether the heliopause data, the direct measurement of the local interstellar magnetic field and plasma density, changes how you think about the Earth's environment. Tell me whether the fact that there is no follow-up mission to the interstellar medium currently funded or planned makes you optimistic or pessimistic about humanity's scientific ambitions. And subscribe if you want to keep going into the places where the most distant data ever collected by a human-made instrument meets the physics that makes that distance so significant.